Hi guys, welcome to tutorial for aromatics and amines. Let's look at the learning outcomes. Number one, you must be able to describe the mechanism of electrophilic substitutions in aromatic compounds. So what is that electrophilic substitutions? Now we learned that electrophilic addition is actually meant for alkenes, the one with the double bonds. Now in this case, aromatic compounds also with double bonds, but why we go through substitutions rather than additions? Okay, because of the delocalized pi system. So within the benzene ring, there are three delocalized pi electrons, or three double bonds, or three pi bonds, actually freely rotate or delocalize within the ring, and that will stabilize the overall benzene ring structure. And that's the reason why whatever reaction they go through, it will be substitution because they are trying to maintain the delocalized pi system. All right. So for the second one, able to describe the chemistry of aromatic compounds as exemplified by the following reactions of benzene and metabenzene, such as substitutions reactions of chlorine or bromine, nitration, oxidations of alkyl benzene with 2-carboxylic acid. Okay, the third one, able to describe the chemistry of phenol as exemplified by the following reactions with bases. How does it react with base for phenol, and how does it react with sodium? How does it get nitrated, and how does it get brominations? All right. And the fourth one is able to explain the relative acidities of water, phenol, and alcohol. So this is just a comparison, which I've discussed it in class, right? So next one is able to describe the formations of amine, how to get amine, or even phenylamine. Phenylamine is actually the benzene ring together with an NH2. So able to explain the relative basicities of amine, phenylamines, and ammonia. Again, I've explained that in class as well. You must be able to describe why amine is more basic than phenylamine. So the reason will be always in terms of electron donating group and electron withdrawing group, EDG and EWG. And the last, able to describe the reactions of amines and phenylamines. Right? Let's look at the first questions. Name the following compounds. Now for A, it's actually a normal amines with 1, 2, 3, 4, 5 carbons, so is pentylamine. Okay, so oops, what am I doing? My bad. Pentylamines. All right, and the next one is actually a branch. Let me draw it out in a proper way. So you have a CH3, CH2, CH2 attached to NH, and then you have another one, the same thing, CH3, CH2, CH2. Now, obviously, in this case, we still name it as amines because you have an N nitrogen there, NH, or tertiary, primary, secondary, right? So we have to look at that. So in this case, it's obviously a secondary structure, and we have two propyl group because of 3 carbons. So we can just name it as dipropyl amines. All right, as simple as that. And the last one is actually CH3CH2. This is actually C2H5 with NH3 positive, Cl negative. Now, this is actually a salt. So this is a quaternary structure, which means your nitrogen is actually forming 4 covalent bonds by donating its lone pair away. So in this case, how do we name that? It's actually same thing, 2 carbons, so it's ethyl, but not amine, is ethyl ammonium now because of the positive charge. It's a salt now, ammonium chloride. So ethyl ammonium chloride. So that's the name for the part 3. So this is actually a quaternary ammonium salt. So always remember that primary is the nitrogen is still having 3 bonding. Same goes for secondary and tertiary. They're still maintaining a 3 bonding and 1 lone pair. The only difference is that primary has no R group or just 1 R group, secondary 2 R groups, tertiary 3 R groups. But for quaternary structure, it is actually having 4 covalent bonds, 0 lone pair, because you have donated the lone pair to form additive bonds to a H or another thing. So you get a quaternary ammonium salt. All right. So these are the name for part A. And then for part B, let me erase that. So for part B, predict whether diethylamine is actually a stronger or weaker base than ethylamine. So let's try this. Diethylamine. So basically you have NH, diethyl meaning that you have two R group, two ethyl group. So it's CH3CH2, CH3CH2. All right, that's diethylamine. And ethylamine is just as simple as one ethyl group and H2. So one is a secondary structure, one is a primary structure, right? This is a secondary amines, this is a primary amines. Now let's look at that. In terms of basicity, we are looking at nitrogen as a proton acceptor, the electron density of it. So nitrogen will have lone pair here, same goes to this. Both are actually having lone pair. That's why they still can consider as a base because they can accept proton as a proton acceptor by using its lone pair. But then in this case, the only difference between them is the number of R groups, right? And R groups or alkyl group, we call that as electron donating, right? These are all electron donating group, EDG. And electron donating group will tend to actually donate electron towards the nitrogen, increase the electron density of nitrogen, hence making it more likely as a proton acceptor. Because nitrogen now, as a result of getting electron density from all the electron donating group, it is rich in electrons, so they can act as a better proton acceptor. So in other words, it is a stronger base. So in this case, obviously the secondary amines, in this case, the diethylamine has two electron donating groups, hence making it more electron rich. Therefore, diethylamine is a stronger base than ethylamine. It's about the number of electron donating group. All right, so that's the answer for part B. Okay, question 2. Give a region and conditions needed to make a butylamine from butane nitrile. And of course, by name, you must able to draw the structure out. Let's look at part A1. Okay, so first, they want to make butylamine, which is an amine from a butane nitrile. So butane nitrile is actually 4 carbon, is a nitrile, nitrile meaning that is having a CN. This carbon is counted. So CH3, CH2, CH2, 3 carbons already, and then CN. So altogether 4 carbons, butane nitrile, and they want to change it into butylamine. So same thing, CH3, CH2, 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 NH2. So this is butylamine, 4 carbon with an NH2. Now, if you can see that, right? Let me change this. Now, the difference between these two structures will be this. Same number of carbon, is just that the CN now has turned into CH2 and NH2. So basically, I've added 4 hydrogen into it, into the CN, all right? 2 hydrogen each. Then you are getting this butylamine. And when you're adding hydrogen into an organic molecule or into a compound, we call that as reduction. So this is actually a reductions reaction. So if it is a reduction, of course, we will need a reducing agent. And what are a reducing agent we can use? LiAlH4, lithium aluminum hydride in dry ether. Either this or NaBH4 in alcohol. So either one can be used as a reducing agent, then you will get a nitrile convert into amine. All right, so you're just adding 4 hydrogen atoms into the CN so that you get a butylamine. So this is the answer for part A1. All right, let's look at part A2. Name the bromoalkane that can be used to make the butane nitrile, which means we are trying to make this thing, the butane nitrile, before we can get the amine. So what bromoalkanes can be used to get that? So you see, CN is obviously a nucleophile. So in this case, they want bromoalkane. What bromoalkane would you suggest? It's actually bromopropane, Br. See, initially I should have 3 carbons, 1, 2, 3 with a Br. After that, I'm going to react with KCN in ethanol, ethanolic KCN. So this CN here will act as a nucleophile and substitute the Br and turn it into CN. And that's how you get butane nitrile. All right. So always remember when you react with KCN in ethanol, especially this reagent, it means you're giving an additional carbon to the molecule. So initially started with 3 carbons. At the end, you will get 4 carbon, including the carbon from the CN group, right? So you have additional carbon. So in whatever reactions you can see, whenever there is an additional carbon, it's always using KCN in ethanol. That's the shortcut you can do, right? So that's for question 2. And let's look at question 3. Write an equations for the reactions of chlorine with benzene in the presence of iron 3 catalyst. Iron 3 chloride is actually FeCl3. This is the same equivalent to AlCl3. And what are they? They actually halogen carrier, right? I mentioned that in class. So these are halogen carrier. They're responsible to grab the halogens so that they polarize the chlorine into a Cl positive, and the Cl positive will actually attack the benzene ring as a strong electrophile. Okay, so what equations they want here for the reactions of chlorine with benzene in the presence of that? So they just want a general equation, not the mechanism. So for part A, you may just write a benzene, right, plus a chlorine gas, okay, and plus FeCl3 to form this, substituted with Cl and plus with suppose. So what are the products? Supposed to be FeCl 4 minus plus H plus. You see that? So this is the balance equations. All right. So this is what they want. And then for part, before that, let's check this again, guys. Just a reminder for you, what's happening between these two, the halogen carrier and the chlorine. So let me write an additional equations here. FeCl3 is actually reacting with ClCl. Like I said, it polarizes it, right? So it will turn into FeCl4 minus, it grabs one of the Cl together with the bonds, like that. So the remaining Cl will turn into a Cl positive as a strong electrophile in order to attack the benzene ring through electrophilic substitution. And why do we need that? Why do we need a stronger electrophile? Because benzene ring is stabilized by its delocalized pi system. Okay, so that's why we need a halogen carrier in this case, right? So that is for part A, right? And look at B. What do we call the mechanisms of reactions in part A? Electrophilic substitution, guys. Electrophilic substitution, ES, right? Just a short form. And for C, draw the mechanisms of reactions in part A with Cl positive as the attacking species. So you don't have to give the detailed things, you just start with this. So the mechanism for part C would be a benzene ring plus a Cl positive straight away as an attacking species, which is the electrophile. And then the curly arrow always from double bond of the ring to the electrophile. And then what do you get? You get the intermediate. The intermediate will have a smiley face. And then you have your origin of H is originally there. And then you have a newly added Cl. And what happened now is substitute the H. So the bond, the CH bond here will break and move it in. You have to show the curly arrow. So then you will get a substituted benzene ring called a chlorobenzene. So the name for this is chlorobenzene. And then you have your H plus being substituted away. So that is the full mechanism. All right, you have two curly arrow, 1 and 2. That's enough for the curly arrow. Okay, that's for C. And let's look at part D. So draw the display formula of the tri-substituted halogen arenes produced if methylbenzene is added to excess of bromine at room temperature in the presence of iron 3 bromide. Now methylbenzene is something like that, CH3 attached to a benzene ring. That's what we call a methylbenzene. And when you react with bromine in excess, and in the presence of Fe3Br. Now again, Fe3Br, what is that for? FeBr3, this is the formula, and this is actually again as a halogen carrier. And why do we need a halogen carrier? Because we want to polarize the bromine so that the bromine will form a strong electrophile, Br positive, so that it can attack the ring. And in this case, it says that you will form a tri-substituted. What does that mean by tri-substituted? Instead of one bromine gets in, you have 3 bromines trying to substitute into the ring. Okay, and what product would you get when you tri-substituted it? Bromine with FeBr3 as a halogen carrier. All right, I'm just drawing the equations. So what would you get is this is a CH3, right? in order to determine the position of bromine that will attach to the benzene ring, which position they will attach to. It all depends on the group that pre-attached to the ring. In this case, the group that pre-attached to the ring is actually an electron donating group, EDG, which directing to 2, 4, and 6, right? So therefore, the product, the tri-substituted product will have CH3 as well, and 2, 4, 6, you have 3 bromine tri-substituted in. Okay, so this is what they want for part D. This is the formula they want. A tri-substituted bromine. So what do we call that? It's actually a 2, 4, 6, the position of the BR, tribromo methyl benzene. Simple. Okay, tribromo methyl benzene. That is for the D. Okay, shall we look at the part E? So how would the reaction in part D differ if the methylbenzene and bromine were boiled in the presence of ultraviolet light? Now, in the presence of UV light, it would be totally different. And why is that so? Because in the presence of UV light, the bromine will actually turn into free radicals. And still remember that if you have a methylbenzene, you have a CH3 here, a methyl group and a benzene ring. When you have a free radicals, let's say Br radicals, it will not attack the ring in the first place. It will actually attack the methyl group here. And then what do you get? Right? What do you get? So you will get this instead. You will not go into the ring, but you will get a CH2Br. And of course, it is possible to further substitute. It's a free radical substitutions. It will further substitute. You can get, or you may get this CHBr2, or you may get further substitute. You get CBr3. You substitute all the H from the CH3. So these are the possibilities, or these are the possible products formed in the presence of UV light with bromine. Okay, so that's for E. And for F, name the mechanisms of reactions in part E. Like I mentioned, it's under free radical substitutions. Like what happened to the alkane? That's what we learned, right? As long as you have UV light, you have free radicals, they will undergo free radical substitutions. That's the answer for F. Okay, question 4. Place the following molecules in the order of acidity, starting with the most acidic. So the most acidic, obviously, I'll put that in numbers. So number 1 is the most acidic. And then it followed by carboxylic acid, right? And then it follows by a phenol. Don't forget, phenol is a very weak acid, even weaker than carboxylic acid, right? So that's why it's number 3. And of course, number 4 will be water. Water can be slightly acidic sometimes, but then usually it is neutral. And then the last one is alcohol. Why alcohol put at the last, knowing that water is neutral, right? Alcohol is not even considered as an acid or base. It is non-acidic. Water sometimes it still can be if you produce slightly more hydrogen than OH, but that will happen only when you have other compounds in it, like you disinfect the water with chlorine or fluorine. That will make it slightly acidic. But alcohol, no matter what acid, whatever anything is you put it, it won't react with it, right? So you will still be non-acidic or non-basic. So alcohol will always put at last. So in this case, this is the sequence in terms of acidity. And of course, you don't need to actually explain that because they just want you to place the order. All right. So for part B then, would you expect methanol to be more or less acidic than phenol? This is not actually a good question. In fact, like I explained for propanol here, methanol is still an alcohol. It is non-acidic at all. So obviously in this case, phenol compared with methanol. Okay, let me re-explain again. How do we do that, right? So let's look at the group attached to the OH. Now, in order to act as an acid, right, this is the group attached to the OH. This is the group attached to the OH. So we are talking about the feasibility of the OH to break, or the dissociation of the OH to form H+. All right, if there is dissociation to form H+, meaning that it's more acidic. All right, so in this case, benzene is EWG, since OH is EDG, okay, the complement. And this is EDG for the alkyl groups. Now, let me explain again. When you have EWG, it will withdraw electrons from the oxygen. Oxygen will become low electron density. And therefore, the bond between OH will be weaker, hence favor the dissociations of H plus. Okay, favor the dissociation of H plus. That's the reason why phenol is actually more acidic than methanol. And why methanol is non-acidic? Because it attached, the OH attached to the electron donating group. It donates electrons to the oxygen. Oxygen will have high electron density. When you have high electron density for oxygens, the OH bond, knowing that this delta negative, this delta positive, right? So the OH bond is much stronger bond. So when it's much stronger, it is less likely to dissociate, less likely or impossible for it to dissociate because you need to have high bond energy to break it. So no dissociation, meaning that it is non-acidic at all. So this is how we explain that. All right. Okay, question 5. So phenol is an aryl compound or aryl compound. What does that mean? Aryl compound. Aryl compound means any compounds that with benzene. So knowing that the structure of phenol is actually a benzene ring with OH group, so that's why they call it an aryl compound. All right, let's look at part A1. What is the molecular formula of phenol? Not that molecular formula is C6H6O. That's the molecular formula. Always remember, molecular formula means you're trying to present it to people that how many carbons in total, hydrogen and oxygen. Just put that. So a molecular formula is meaningless in terms of the arrangement. It tells us nothing about how they arrange in a structure. All right, C6H6O, it can be arranged in straight chain, ring, or whatever. So no information at all. But then in structural formula, yes. In display formula, yes. In skeletal formula, yes. We can see how the carbon arranged. Like in this case, this is like a skeletal formula in a way. So you can see they're arranged in a ring, hexagonal ring with an OH group, right? So this is part A. And let's look at part A2. All right. So what is the empirical formula of phenol? Same thing, C6H6O. C6H6O. You can't get the simplest formula. That is the simplest formula. So same thing, C6H6O, unless you have 6 oxygen, right? Then you get CHO. But yeah, same answer. And part B, molten phenol reacts with sodium metal. Give one observations and write a balance equation for the reactions happen. So for B, right, we know that phenol is actually having an OH group. So OH group is something like an alcohol. It will react with sodium as usual, as normal alcohol. And what you get here is you will get O negative and A positive, sodium phenoxide plus hydrogen gas. Okay, exactly like what it happened with other alcohols. So this is how it looks like. And they want to give observations. So what observations? Hydrogen gas release. Okay, effervescence or gas bubbles. This is the balance equation then. Okay, so next one, part C. Let me erase that. You get. So for part C, phenol reacts with sodium hydroxide. Again, phenol is acidic, right? It is slightly acidic, pH 6.5, and then it will definitely react with sodium hydroxide, which is a base, and neutralization take place. You will get the same sodium phenoxide plus water, no hydrogen gas because it's neutralization in this case. And then, yeah, that's the balance equations. Okay, oops, sorry. Name the type of reaction, neutralization, and write a balance equation, which we have done it. That's for C. Okay, and for D, the reactions in part B and C both give the same organic compound. Name it. Sodium phenoxide. Right? Phenoxide. It's a phenol, but now it turned into O minus. That's why it's oxide, so phenoxide, and you have a sodium attached to it, so sodium phenoxide. Part E. Phenol reacts with bromine water. Give the name of the product, 2 visual observations and balance equations. Comment on how these show the phenol is more reactive than benzene. Okay, let's do it one by one. So give the name of the product. Let me show you the balance equation first, right? So when you have phenol, I've shown you in the class, phenol same as phenylamine, exactly the same. When it can react with bromine at room temperature, and then you get a tri-substituted bromine. Okay, 2,4,6 tribromophenol. Okay, 2,4,6 tribromophenol, and this is actually a white precipitate. Okay, so balance equation is there, I guess. Wait, no, it's not. So plus with 3HBr. Now, obviously, this is electrophilic substitution for benzene always, and you substituted 3H out. So in total, you have 3 bromine here. So 6 bromine atoms. 3 substituted in, another 3 will react with the H plus form to get HBr. So that's a balance equations, and that's the name. And that's also one of the observations, white precipitate. But they need 2 visual observations. What else can we observe? Guys, bromine is brown in color in aqueous form, right? So this brown color will decolorize. So decolorizations of bromine will be the second observations. First, formations of white precipitate. At the same time, you will observe decolorizations of bromine, brown to colorless. Okay, that will be the 2 visual things. And comment on how this shows the phenol is more reactive. Now, if you react with benzene, right? Let's say, for example, if I'm comparing this equation with this. Now, you see that? If it is a phenol, you can react with bromine even at room temperature to form a tri-substituted product. But if you have a pure benzene with bromine, do you think it works at room temperature? Never. You will need one thing called halogen carrier, which is a catalyst. You will need catalyst for it to react. You will need to heat it up. Okay, you will need to heat it up because it's an organic reaction, mostly heat it up. But then for phenol, phenol is much more reactive so that it can happen at room temperature without any halogen carrier. See that? So they want you to comment, so just write it out. Okay, and why phenol is actually more reactive? Why phenol is more reactive than benzene? Because phenol is having a electron donating group EDG attached to it. EDG will provide electrons, will donate electron to the ring, and it activates the ring by providing more electrons. See that? Benzene ring itself, why would it react with other things? Because it is electron rich. Therefore, it is electrophilic reactions. It will attract electrophile because it's electron rich. Imagine that you have an OH group attached to the benzene ring. It donates more electron to it. It donates more electron density to the ring and making it more electron rich. See that? So it's more susceptible to electrophilic attack. Okay, it is more susceptible to the electrophilic attack. That's for it is more reactive. Okay, all right. So let's move on. That's part E. Part F. Explain why phenol is more reactive than benzene. I just explained that, right? So phenol have an OH group attached to it. So OH is electron donating. Let me repeat that again. Phenol has an OH group attached to it, knowing that phenol is electron donating, so it activates the ring, making it more electron rich. Therefore, it is susceptible to electrophilic attack. So this is the answer. All right, for F. Move on, last questions. Okay, benzene can be nitrated to give nitrobenzene. Name the mechanism for this reaction. Regardless, it's always electrophilic substitution, always, right? Other except for oxidations. Yeah, that's a different case. All right, part B, because if it is oxidations, right, it will be more obvious. You will have KMNO4 and K2Cl2O7 in the questions. So if you see oxidizing agent, of course, it's oxidations, right? Common sense. But then if it is not, benzene will always undergo electrophilic substitutions reaction. Let's look at part B. Now, the species attacking benzene in the anode is NO2 positive, obviously, because we are putting NO2 into it. How is this generated in a reaction mixture? Name the substance used to give a chemical equation for the formations of NO2. So what they want is how you generate the NO2 positive. It is actually with the reagent. What reagent is that? Concentrated sulfuric acid plus concentrated nitric acid, right? When you mix these two together, they will react. This is an acid, this is a base. In fact, it's an acid-base reaction. So why? Because you will get HSO4 minus proton donor. See that? And then What you get next is you get NO2 positive, you get H2O, right? So the H is actually going to the O in a way. So this is in a way as a proton acceptor. Of course, it's not that obvious, but then yeah, the H from here will go to the H with this H combined. You have H2, take one O from here, you get H2O. So it's still a proton acceptor anyway. So that's how you generate this NO2 positive. So this is the equation they want. All right. So part C. Let me erase the rest. Okay, part C, suggest a suitable temperature for these reactions. So what is that? Suitable temperature. So for this nitration, or you're putting NO2 into it, right? I remember I wrote it down on the board. It is actually less than 55 degrees Celsius. So you have to remember that 55 degrees Celsius always, or less than 60, that would do. Okay. So this is the temperature, which is the answer for this. And part D, use curly arrow to show the mechanisms of how benzene react with the NO2 positive. Again, it's under electrophilic substitutions. You have a benzene ring with NO2 positive, right? And curly arrow from here, benzene ring, double bond to the positive, and then you get a smiley face, incomplete ring in it. H here originally there, NO2, and now pull in the CH bond so that you get back your delocalized pi system, stabilize it, and then you have your NO2 attached to it plus H plus. So this is the balance mechanism for part D. All right, and that's all about it for this tutorial. I'll make it simple because this thing, it's actually a lot in the syllabus. In fact, for benzene, I'm not in the syllabus as in organic chem. Benzene, there's a lot more to learn. You have sulfonations, you have a lot of things to learn. But in this foundation level, we just squeeze it into this, the main reactions that you need to know, the crucial ones, right? Thank you for watching this. Good luck, right?